All right, let's take a look at this problem. Honestly, it's not too difficult, with the exception of it has a lot of weird units in it. Like, notice that one of the questions asks for an answer in revolutions per minute squared. Another one wants units in millimeters per second squared. So, if you did something and you felt like your work was right, one of the things that you might want to check right off the bat is your units. Are your units? Okay, so here we go. It says, the flywheel of a steam engine runs with a constant angular speed of, so a constant angular speed would be this, and that is 279 revolutions per minute. That's my number. That may not be your number. When the steam When steam is shut off, the friction of the bearings stops the wheel. So this must be like the initial velocity. And we are going to be stopping the wheel due to friction. And we're going to bring the wheel to stop in a time of 2 hours. And question A says, what is the constant angular acceleration? What is the acceleration? Question mark. In revolutions per minute squared. So since I have to give my answer in revs per minute squared, and I already have revs per minute, I think I'm just going to change time into minutes. So 2 hours, 2 times 60 would be, so I'll say times 60, that's going to be 120 minutes. All right, so how am I going to find the acceleration? How about this? So the final velocity equals the initial velocity plus the acceleration times time. We are bringing the wheel to rest. It is starting at 279. So I'm going to solve for alpha, and I know that this is 120 minutes. So you can see that we're going to bring the 279 over, and my alpha answer should turn out to be negative, and I get 2.33 revs per minute squared. And you can see that answer is correct, 2.33 revs per minute squared. So if my steam engine is running counterclockwise, and the steam is supposed to be like acting like friction to slow it down, that obviously must be happening in a clockwise direction to counteract that. All right, letter B says, how many revolutions does the wheel make before stopping? And they want the answer in rotations, which a rotation is a revolution. So I think we're okay with that. So I'm just going to stick with my minute revolutions in my minutes. I guess it doesn't really matter. So we'll do this. 2 alpha and theta. We are stopping it, and we are starting at 279 squared. This is going to be a 2. This is actually a negative 2.33 because it's slowing down, and we're solving for theta. And when I solved for theta, I got 16,704 revolutions, which, with rounding off significant figures, is in that ballpark. All right, the next question. At the instant the flywheel is turning 75 revs per minute, because realize it's slowing down. It's starting at 279 and it's going down to 0. So at some point, it's going to pass the 75 revs per minute. What is the tangential component of the linear acceleration of a flywheel particle that is 50 centimeters from the axis of rotation? Well, there's kind of a lot going on there. All right, so let's start by drawing a picture of what that just said. So we're moving on to part C. And I'm going to draw this picture kind of big so that I can kind of see it. All right, so we have a particle that is 50 centimeters from the axis of rotation. So I'm going to say R equals, I'll say 0.5 meters. And so this is the particle. We'll make the particle a different color so we can kind of see it better. All right, so there's our particle. All right, at the instant the wheel is going 75 revs per minute, I think I'm going to write that number down. So W is 75 revs per minute. What is the tangential component of the linear acceleration? What is the tangential component? So that's like a tan. What is a tan? What is a tan? So a tan is equal to R alpha. But the issue is they want the tangential component in the units of, which it should be normally meters per second squared. They want millimeters per second squared. So I'm going to have to play with that a little bit. So I got to talk through these units here for a minute because I think this could be the confusing part for some people. If I did the acceleration in radians per second squared, and I did this radius not in meters, but in millimeters, remember that a radian is a nothing unit. So on this side, I have millimeters per second squared, and that's what I need over here, millimeters per second squared. So that just tells me that what I need to plug in here is I need to plug in the radius, not in meters, but in millimeters. So 0.5 meters, to turn that into millimeters, I'm going to move my decimal point over 3. That's going to be 500 millimeters. Now I have to plug in alpha, which we actually just found. We found alpha up here. But the problem is alpha up here is in revs per minute squared, and I need it in radians per second squared. So that's just kind of annoying, but it's just a conversion that we have to do. So let's go do that down here. So we will take 2.33 revs per minute squared. That squared is important. All right, 1 rev is going to be 2 pi radians. So I have my revs cancel. I got my radians. But now I have minutes squared. So I can take care of one of them by going 1 minute is 60 seconds. That would cancel the squared with that minute, but I still have another minute. So I got to do it again. 1 minute is 60 seconds. And now my second minute will cancel. And look what's left. Radians per second, radians per second squared. So I just have to multiply all this out. And so let me find a calculator. Here's one. All right, so we have 2.33 times 2 times pi. And then we're going to divide by 60, and we're going to divide by 60 again. And we get 0.00. When I have a really small number in WebAssign, I've learned to keep a lot of decimal places. So 0.0040, and it's 4066, so I'll say 7. All right, that number is the angular acceleration in radians per second squared. That's what I need to plug in right here. So I'm going to take that number, 0.00407. I'm kind of running out of space here. And equals. So I'll take that number, and I'm going to multiply it by 500. And there's my ATAN, 2.033. ATAN is 2.033 radians per second. Whoops, I'm sorry, millimeters per second squared. Let's circle all of that. All right, 2.033 And that looks good. That looks good. All right, the last question. What is the magnitude of the net linear acceleration of the particle in point C? All right, so what is the magnitude? So I don't have to find the direction. I don't have to find the angle. But what is the net linear acceleration? So the net linear acceleration is made up of an A tan, and I'm going to write in the A tan. So A tan, and that number is 2.0. Whoops, I take that back. That is not correct. Hold that thought. Hold that thought. All right, so I have to draw another picture because I'm out of space. Okay. So the net linear acceleration is made up of an A tan. And I do have A tan, but I kind of have A tan in weird units here. So I'm just going to write that down. I have A tan 2.033, but that's millimeters per second squared. That's not going to be really useful to me because they want the net linear acceleration in meters per second squared. So let's handle that right away. So in order to get A tan in meters per second squared, I'm going to have to make sure that my R is in meters in this equation. So I'm kind of going back and doing what I just did, but I'm doing it now with the new units. All right, so I want my acceleration in radians per second squared. We did that. That was this. So I'm going to plug that number in, 0.00407. And this time I need my radius to be in not millimeters, but meters. So I'm going to put 0.5. And now I'm going to number crunch to find A tan. So that is going to be 0.00407 times 0.5. And that is A tan 0.02035. Now I'm going to write this on my picture. All right, so A tan is 0.02035 meters per second squared. All right, but we are trying to find the net linear acceleration, which is made up of an A tan and the centripetal acceleration, AC. I just got to figure out what the centripetal acceleration is now. This problem is kind of long and involved, but I kind of like it. All right, centripetal acceleration is going to be equal to V squared over R. Remember, I need everything to be in meters and seconds. We know what R is. It's going to be 0.5 meters. I got to figure out what V is. That's where this comes into play. That we are talking about the particle at the exact moment that it's going at 75 revs per minute. I got to turn W into V. I got to turn 75 revs per minute into meters per second. How about this? V equals RW. So, except when I do V equals RW, this W has to be in radians per second. So I'm going to pause for a second and take 75 revs per minute. And I'm going to convert this into radians per second. 1 rev is 2 pi radians. Why I kind of like this problem is it really makes you think about what are the units that things are supposed to be in and what are those relationships. 1 minute is 60 seconds. Cancel, cancel. So how many radians per second do we have? 75 times 2 times pi divided by 60. I get 7.85 radians per second. So that's what I'm going to put here. 7.85 radians per second, because I got to have radians to use this equation. The radius is 0.5 meters, so 0.5. So now I can figure out what V is. So I'm going to take the answer in my calculator screen times 0.5, and V is 3.9, I'll say 27 meters per second. All right, so now that I know the velocity in meters per second, I can plug that in up here. That's 3.927 squared. All right, so we will square that number, divide by 0.5, and I get a centripetal acceleration of 30.84 meters per second squared. I'm going to add that to my picture. Add that to the picture now. So 30.84. This one is 30.84. And now to find the net linear acceleration, I have to, this is obviously not drawn to scale. This arrow stands for 30, and this arrow is supposed to be 0.002. So big time not to scale, but since I already have my arrows here, I'm going to go for it. And I have to Pythagorean theorem this now, and this right here, C, I'm going to label it C. C equals the net linear acceleration. So little a squared plus b squared, you can tell that my C is not going to be too much bigger than 30.84, but we'll square that, plus 0.002035 squared, and then we'll square root it, and we get 30.8425. So we'll take it. 30.8425 meters per second squared. All right, and they have 30.9. Close enough. Close enough. All right, I can definitely see why people might have gotten stuck on this problem. So I hope the video helped you finish yours. Thank you for watching.